Hello everyone, this is Marmoush and today I'm presenting a numerical simulation of wave-driven flows on a morphologically evolving beach. This study is part of my PhD research during my stay at Queen's University under supervision of Dr. Ryan Mulligan. So starting with the introduction, a two-dimensional physical model have been used in this research to simulate the beach morphologically changes during a storm. So in the basin, we were able to simulate a storm by varying the wave condition at the wave pedal. Also, in order to capture the change in the beach morphology, we used a laser scanner surveys several times after each storm phase. In addition to both, we've been using a single transit location to collect wave and velocity measurements. Unfortunately, in this research or in the physical lab, we were not able to measure the alongshore flow measurements, so no measurements along the beach. And that's the aim of the study, is using a numerical model that first calibrated with the measurements that we have across the beach profile. And once the model is calibrated, we aim to use the same model to investigate the nearshore wave-driven flow circulation in order to understand how the change in the flow circulation is able to match with what we measured in the sediment transfer patterns. So starting with the physical model, we've been using a wave basin. It's 26 by 21 dimensions, and there's a beach of 20-meter long steep sandy beach sitting in the left side. On the other side, in the right one, you can see 11-meter long wave pedal able to generate on the unidirectional random wave pedal wave signals. And as you can see, there is a point called W4. This is where we have measurements in front of the pedal. For this point, we have done 5 wave signals, and the wave signals are presented in this plot. As you can see, starting with the first signal we made, it has a low energy but for long duration, almost 20 minutes. And this is simulating when the storm passing across the beach. This is where the storm is kind of far away from the beach. And as long as the storm keep approaching the beach, the wave energies are increasing from S1 to S2 and then S3. And also the durations are increasing from 20 to 15 to 10 minutes. So the maximum wave heights and the shortest wave duration is where we are simulating the storm is in front of the beach. And once the storm starts to leave the beach, the wave energies are getting low again, giving 8 centimeters and then almost 6 centimeters wave height for longer duration. This is how we simulated the wave storm. The same information is presented in the right side with spectral distributions and giving the same information. Also, we've been using, after each wave signal, we've been using a LiDAR scanner that we had first to stop the waves, drain the basin, and scan the beach from 3 different angles in order to get 3 different information with point clouds. All these information or point clouds are eventually merged in one map to visualize the beach elevations. And this is what we had at the end. At the right side, you can see a map of the beach at different times or phases of the storm. So M1 is before running any waves, and then M2 after running the first S1 signal, and M3 is after running the S2 signal, and so on. In order to understand the change in the map, we substitute each map by the one before. So you can see in the left column the different maps indicating erosion deposition processes, where the erosion is indicated in red and deposition is indicated by blue color. At the end, or the lowest plot, you can see the integrated beach morphological change indicating the entire erosion deposition areas. Last thing was the wave and flow measurements we have across the beach. So we had 5 pressure sensors in addition to 1 wave gauge working at 16 to 50 hertz, giving the wave information across the beach. In addition to 3 velocity sensors located, as you can see in the plot, with across the beach transit. Okay, now it's the numerical model setup. So we've been using SWASH model, which is non-hydrostatic wave flow model. The computational grid was designed to 15.8 multiplied by 14.7 meters, and the cell grid size was 2.5 multiplied by 2.5 centimeters. A very fine grid resolution, horizontal resolution. And also we've been using 2 vertical layers, which was sufficient in this case to capture the vertical distributions. At the offshore boundary forcing condition, we've been using reflective or weakly reflective offshore boundary, and at the sides we've been using observing boundary conditions. The coordinate number was set to around 0.5. Okay, in this slide I'm comparing the wave measurements to simulations in order to calibrate the model. So here, as you can see, the model was able to generally capture the wave transformation process accurately in all the signals. However, the model still overestimates the wave height slightly outside the surf zone. When it's getting into the shoaling zone, the model is doing better job giving better matching. However, when it's about to reach the breaking onset, the model underestimates the high energies, especially the high energies. However, it still predicts the breaking location accurately. Different way, same information is given here by the spectral analysis of measured and simulated waves. As you can see in the spectra comparison, there is a prediction of peak frequencies. At the same time, there is a slight change in the spectral shape, which is expected for different reasons. However, it's still giving almost similar energies. On the other hand, comparing the velocity measurements with the simulations, SWASH is still capturing the increase of the alongshore current induced by the wave breaking accurately towards the beach. However, the values is overestimated, especially when it's close to the breaking location. The model also over-predicts the surf zone width. And one important information we have to say here is that the model is not perfectly simulating the real case in the lab, because the SWASH model simulates only fixed bottom, where in the lab we were investigating or examining movable beach slopes that can have an effect on the results. Also, that the model simulation time has been fixed over all storms. However, in the lab we've been doing each storm signal with a different duration. We've done a sensitivity analysis in order to see what if we change the default values of SWASH for the most important coefficients. We know that they make a difference or can make a difference, such as bottom friction, horizontal eddy viscosity, or breaking activation parameters, and end up that we realize that default values are giving the most accurate assumptions for this case. In this plot, we are showing, once we know that the model is in acceptable level of calibration, different time averaging domains, for example, wave breaking. And as you can see, waves are breaking almost pretty close to the shoal line. And there's a wave setup indicating the wave set down and followed by the wave set up pretty close to the shore. Also the kinematic energy distribution and the breaking fraction, where waves are mostly breaking. That's in line with the first plot of the significant wave height. Also the flow velocity and the viscosity domains. This plot shows the paper or the study conclusion, where we can see in the left column you can see the alongshore current field. So in S1, as you can see, high speeds are just generated next to the shore line, and the surf zone width is kind of narrow. And by increasing the wave height from S1 to S2, the surf zone width is increasing and speeds are getting higher. When it jumps up to this S3, giving the highest wave energy, you can see that the speed is high across the whole width of the surf zone, which is giving the widest case of surface zone widths of a longshore current. Using such information, we've been able to calculate the critical bottom shear stress, where sediments have initial ability to move, and this is what we've plotted in the right column. So you can see in the yellow colors, this is where sediments are most likely are about to transport, and this is confirms that the model is doing a good job predicting the shoreline retreat. So as you can see from the maps indicated by contours, that yellow color is just next to the zero contour indicating the shoreline location. And every time the wave energy is increasing, the area of yellow and light blue, which is the critical area of sediment transport, is increasing and getting wider and with higher abilities. The most erosive case is definitely with S3, so where you can see a wide spots of yellow color and also light blue. So this was the conclusion, that the model was able to relate between the sediment transport that have been measured in the lab and the simulated flow field from SWASH. Thank you, and that's it. Thanks.